Yeah, thanks for sticking around. I'd like to tell you guys about a project that is just getting underway. We're literally just starting the simulations for this. I'm working on this with a PhD student, Caitlin Watson, my advisor, Alejandro Lejo Flores, and from the U.S. Bureau of Reclamation, Eric Rothwell. So the motivation for this is that water resource managers need accurate and timely forecasts for like precipitation, temperature, winds, and at spatial resolutions, assuming we're talking about Idaho, that resolve that topography, and also at sufficient lead times that allow them to make decisions that are planned out. And right now, what is available for that in the short term, there's widely available deterministic forecasts, and they go out to roughly 10 days. And in the next time frame, 10 to 30 days, which is termed the extended term or intermediate range, there is forecast guidance. Specifically the NCEP CFS, but it's at 5-degree spatial resolution, so that's roughly 50 kilometers. If you want to talk about what's happening in a city or a suburb, that's maybe going to give you one data point there. So that's not sufficient for water management, especially in, mountainous regions. And then there is longer term forecasts. These tend to be even coarser and more statistically based. So our interest is in this intermediate range, but the spatial resolution that's currently available is not acceptable. So this project is really an exploratory research project, and the strategy we're taking is using a regional numerical weather prediction model to dynamically downscale coarse resolution gridded data. And the numerical model we'll use that is the WRF model, and we're going to use the NCEP CFS version 2 data. And there's two parts to this research. The first will consist of some case studies, and we'll analyze a few wet years, a few dry years, and I think more importantly from the feedback we got from stakeholders, and I'll get into that, is analyzing some extreme precipitation events. The next, I put quotes around operational because it's kind of research operational. We're going to, in the, they're starting now, but for the kind of demanding part of the water year, we're going to issue bi-weekly 30-day forecasts, and we will end up then providing a hydro forecast product, and that will be available through a web user interface. I want to kind of step to the side right now and talk about community outreach portion of this project, and it is our stakeholder engagement. We had our first meeting October 13th of this year and invited as many members of the local hydrological community that would come, and you can see representatives from these groups were there. And it was about an hour and a half. We presented our current plan and then solicited feedback. And Dr. Jen Schneider, who is a colleague of Dr. Flores from the Department of Public Policy and Administration, has been very helpful in collaborating with us on this and helping this be a successful engagement process. So the main outcomes of the meeting, we went in with kind of questions and looking for input on what operators wanted. Do you want, is 3 kilometer resolution okay, or do you need to go down to 1 kilometer? Do you want to see dew point depression versus specific humidity? How do you want the GUI to look? And we got back a lot of good feedback, but it was different than we thought, and the main thing was we need some measure of confidence in forecast, because what they get is a lot of information, and it's hard to sift through what is good and what is bad. And on that level, there's really high risks. And if your forecast shows something interesting, then if you take a gamble or not, then I guess basically the point is stakes are high. So if they want anything, they want some level of assurance that the forecast is of some quality. As far as what they wanted to see, basin scale statistics. And our response to that feedback, we're going to run more extreme event studies than we had previously planned. And when we do these biweekly hydro forecasts, we're going to do not just the control simulation, we're also going to do a few of the perturbed members, so that we actually have I think they only have 2 or 3 perturbation members, so it will be a small ensemble, but it will be an ensemble nonetheless. And here's a aerial view of some of the outcome of the first extreme precipitation event that we're going to look at, June 2nd through 4th, 2010. This is in Emmett, Idaho, along the Payette River Basin. It caused extensive flooding in this region and in others. And it's from just the preliminary look at it, it seems like it was probably an atmospheric river event. Okay, so now we're going to step back into the modeling portion. So I grabbed this off of the internet. It had a lot of hits for dynamical downscaling. You can see Roger Pilkey Sr.'s webpage. What I want to illustrate is, so we're going to use the lat long grid as I'm looking for the pointer. The lat long lines as kind of the coarse grid, this GCM climate scale, and then the regional climate model scale, or I heard it talk a decision-making scale. And so we want this area of interest to come down to a resolution that is much finer, say 5 kilometers from, say, roughly 50 kilometers. So how do we do that? Dynamically, we do that by using a numerical weather model. And as I mentioned before, we're going to use the WRF, and it stands for Weather Research and Forecasting Model. It's a state-of-the-art, community, open source model used both for research simulations and operational forecasting, as its name implies. It's developed at the National Center for Atmospheric Research in Boulder, Colorado. And it is a dynamical model, so it solves fundamental physical equations involving the time rate of change of variables to get the output. So here is the domain that we're going to use. It encompasses the entire Snake River Basin. And so the brown lines, these are going to represent the coarse grid, where the sort of the GCM scale data is located at each grid point. And then on the inside, we want to get the data at each of these smaller grid points. So the model is initialized, this volume of air, from this coarse resolution, and then the model chugs away, and by chugging away, meaning it solves these equations like conservation of mass, first law of thermodynamics, momentum conservation. It's a tightly coupled system of partial differential equations, so it numerically solves that at each grid point inside. And at each time step, it gets information from the outside along these boundary conditions and incorporates that in. So you obviously can't have a regional model like in a vacuum, or you wouldn't know about, say, a big pressure trough or pressure ridge or something. So that's how, it's a brief description of how dynamical downscaling works. The WRF model was used in the complex topography of the Colorado headwater region. And these papers by Akita et al. And Lau et al. Both describe it. WRF performed favorably, and we based a lot of our choices of physics parameterizations on these papers. Cool. So the first case study, as I mentioned, we're going to use the NCEP, which is National Centers for Environmental Protection, in their Climate Forecast System version 2, CFSV2. Again, is at that half-degree resolution. And we're going to use both the reanalysis and the reforecast. Reanalysis is basically a data assimilation product where a bunch of OBS are all globbed together and then smoothed into the best recreation of what we believe the atmosphere was. And reforecast, we'll just say that it's essentially a retroactively issued forecast. So how these experiments will work is, or for this particular case, we have a timeline in 2010 starting April 10th, and this is our June 2nd through 4th area. We'll start this simulation with WRF forced by the reanalysis data. And so this will give it time to spin up and will give us kind of our best truth of what this event looks like. And then about a month out for each week, we'll start these simulations forced by the reforecast. And so you see we'll have kind of our truth, and then we'll have essentially 4 versions of what happened. And by comparing these 4 with this, we can see not only how well WRF did, but kind of how soon it caught on to it. So the second component is these 30-day forecasts. We'll use the daily issued operational CFSV2 runs, and they have a control run and either 3 or 4 perturbed members. It's going to be getting pretty expensive for us. We'll probably run 2, but we'll run a few perturbed members. And then I have just a screen capture of the Northwest River Forecast Center page where we're going to design, this is kind of what we're going to base our console on. Eric mentioned that the Bureau of Rec guys really like this. And so, we'll have our region, and you'll be able to mouse over like a basin and get some statistics. So to wrap up, we are using a regional numerical weather prediction model to dynamically downscale available extended term forecasts. And sort of the disclaimer first, accuracy of these intermediate range forecasts, these downscaled intermediate range forecasts is not known, which is why we're undertaking this. And it's also computationally expensive in terms of core hours and in terms of data stored. Running on the 1 kilometer grid that we have for our domain right now, it's about 700 gigabytes for a month. So if we're doing multiple simulations of a month at a time, it starts to add up. But this will provide a quantitative hydrometeorologic forecast at this time scale that allows operators to make informed decisions, and at a spatial resolution that resolves topography better. In closing, again, I'd like to acknowledge Dr. Jen Schneider's contribution to this. She's been very helpful. And as well, the funding, thank Bureau of Reclamation for making this happen, and Texas Advanced Computing Center in Austin for the compute and storage. Thank you, and I'll take any questions.
Questions for Matt before I take a couple, or I give a couple. So have you done any control runs yet on this?
No, we haven't.
Okay.
We've been doing, in a separate project, we're using the same model configuration, physics parameterizations, same domain, basically same setup, but we are using the NORM, the North American reanalysis.
Okay, and are you using explicit physics or are you using a convective parameterization scheme?
We're going to have a 3 kilometer grid in potentially 1 kilometer inner domain. And so at 3 kilometers, they kind of say you can turn it off and let it be explicitly resolving, though I don't know that that's totally satisfying, but yeah, so we're not using a physics parameterization.
Okay. Other questions? Just a comment that as you go forward with this, one of the issues that happens between the wharf going from a high-resolution GCM to a very fine-scale initialization, a model like this is you can get quite a bit of boundary instability on it. And that I was wondering if you did your test runs, you might need to find yourself playing with those outer domains so that you can get the domains further out so that once the precip arrives in the basin of interest, some of those boundary layer instabilities or those boundary condition instabilities are resolved. Now, I don't know. You'd have to do test runs to do that, but I know there's a problem with the wharf going to a higher resolution model. So I was just curious. That's why I was curious about that.
Yeah. We haven't done any testing on that yet, but plan to. So.
Okay. There's an aside here. One of the issues that we run into with the weather community and the meteorologists, we've had to deal with this for a long time, is when is high resolution so high that it becomes high resolution garbage versus low resolution garbage. And there's different ways of, you can put garbage in to the model without intending it. And so that was some of the questions I had right there. Were just mostly some of the pitfalls that you can have when you're taking a low resolution global climate model and putting it into a dynamically downscaled framework. It sounds like a great idea, except there's a lot of things that can go wrong along the way. So it's good to see that Boise State's starting to think about this as they start going into a dynamical downscaled for a specific issue like this. So cool, thank you.
Cool, thank you.
All right.